Welcome back, everybody. So let's continue. Just to make something clear, related to the last question asked on Zoom, and also one of you asked in the break, because this might also be a point that was not understood or that I didn't go much into, is that let's take this example. So the map phase, determining the tasks is easy. There is one task for each split. And a split more or less corresponds to an HDFS block, right? So that's going to be an HDFS block gives you a task. An HDFS block gives you a task. We have 1, 2, 3, 4, 6, 5, 6, 7, 8, 9. So in that case, I would have 9 HDFS blocks, and every one of these tasks processes a block, right? So this slot with 3 blocks, this one 2 blocks, and this one 4 blocks, processing executing the map function sequentially on the blocks. Now, in the reduce phase, what do the tasks correspond to? The tasks correspond to some more or less random assignment of the keys to the tasks. In that case, I decided, and that's something, a property of the job, that the user can decide that there will be 5 reduce tasks. What that means is that every key, every intermediate key needs to be assigned randomly, in quotes, to one of these 5 tasks, right? What that means is that for every one, I need to generate a number between 1 and 5 for every key. That is where we use a hash function. We hash the key, and the hash function gives us a number between 1 and 5. Now, what's going to happen is that at the end of after processing the tasks, what the slots do is that they take the keys that come out of the tasks, and they call the hash function. So for each key, they get a number between 1 and 5. And every one of the slots here is going to already prepare 1, 2, 3, 4, 5. They already prepare the intermediate data. That's for reducer task 1, that's for reducer task 2, that's for 3, that's for 4, that's for 5. The same here, they are going to partition the intermediate data in the 5 categories with the hash function, and here also 5. Then what happens is that at the start of the reduce phase, where one reduce task, one reduce task, one reduce task, so 3 of them are basically assigned, the others are not assigned yet at the beginning, but 3 reduce, 1, 2, 3. Let's call them number 1, number 2, number 3. So it means that, for example, this reduce slot is going to connect to this map slot and say, please give me all the intermediate key values corresponding to reduce task number 1. So map slot 1 is going to say, oh yes, I prepared them for you. Here are the intermediate key values that correspond to reduce task number 1. And then this reduce slot is also going to connect to map slot number 2 and request the intermediate key values that receive the number 1, and also from map slot number 3. In fact, that can be done before the reduce phase starts, because that's only downloading. However, in order to start processing here, here, and here, they must wait until they received all intermediate key value pairs. So this is why you can start downloading, but you cannot start processing yet, because you need completeness, complete data, right? So that is the secret. And so the question on Zoom was about how do you do this assignment? Like, yes, it's randomness, in quotes, by means of a hash function. But you know that a hash function is deterministic, right? It seems random, like it's cryptographic properties that makes them hard to predict and so on, and it kind of distributes a bit evenly, but it's still deterministic. If I give you a hash function, it always spits out the same thing. Does it make sense? I hope it should answer the question on Zoom and also our discussion during the break. Awesome. And so that's the connection between this and this. All right, so now, the last thing I wanted to tell you about is when I say one split gives you one task, that is exact. That's always the case. Every split gives you one map task. But when I say that split corresponds to a block, an HDFS block, that is not quite exact. It's something rough. And let me tell you why, right? So here, I did a lot of slides actually that kind of say the same thing, but here, every split gives you a map task. So that is clear. But the problem is with the splits and the blocks. Can anybody tell me why there is a bit of a problem between splits and blocks? That it cannot be that a split exactly corresponds to a block. Can anybody see why? Once you see it, I pretty much done my thing. Let me ask it in two parts. What is an HDFS block? What is the size of an HDFS block? (128 megabytes). So by default, you can change it, right? Could be 64, could be that something you can change. But basically, if you say it's 128 megabytes, that is exact. So it means that if you start writing a file to HDFS, after you have 128 megabytes, that's the end of the block. And you don't even care what's inside the block. 128 megabytes, bam, we cut, that's finished. End of the first block, we start the second block, right? Merciless, without mercy, 128 megabytes, bam, end of the block. So that's at the bits level.
Someone on Zoom had an idea?
Sorry?
Someone on Zoom had an idea for your original question. So they say that the split may need 2 blocks, and these 2 blocks may be spread over different machines.
Yes, exactly. And how could it be that a split is over 2 blocks? That's exactly correct. But why? Just one more thing. Why? Yes, 128 megabytes block limit. Why cannot we say that the split also stops where the block stops? Why can we not say that? Because we could say that, right? We could say yes. Yes, exactly. Because the splits are partitions of key value pairs. The splits are not about bits, they are about key value pairs. So what's going to happen? What's going to happen is that because a block is about bits and a split is about key value pairs, records, synonym for key value pair, what's going to happen is that most of the key values of the split are going to be nicely in the block, but the last key value might start in your block, but then it was merciless cut into, right? And then continues in the next block, right? In fact, the odds that it doesn't happen are very low, right? For a key value to exactly stop here, you have to be incredibly lucky, right? In almost all cases, in majority of cases, the last key value is going to go a little bit into the next block, right? So you're correct, you and also on Zoom, this is the problem. So it means that a split kind of, sort of corresponds to a block, except that the last key value in the split might eat a little bit into the next block. So that's something to be aware of. And what that means is that when you actually locally, we said that the idea is that MapReduce has the map tasks execute locally reading a replica of the block on the same machine. This is not entirely sufficient because you do need one remote read for finishing the split, right? So you might be able to read from the local drive, from the local disk, a replica of that block. But after you're done, the machine might need to connect to another data node just to request the last few bits that you have in here. And the HDFS API allows you to do that. It allows you to say, I want to read a block, but not all of it, just the first bits. Right? That's the idea. So you might need this remote read. All of that MapReduce is doing. It's taking care of it. It's all implemented in a way that this just happens more or less automatically and efficiently. Right? So just wanted you to be aware of that there is this tiny mismatch between the two, but it's taken care of. And that happens almost all the time. Almost every time a split eats a little bit on the next block. Is everybody with me? Right? Any other questions? Because that's the last slide, MapReduce. Anything you've dreamed to ask on MapReduce? on Zoom. This is your opportunity. I mean, you can also still ask questions in the next lecture, but yes? Yes. So the question I'm repeating for those on Zoom, is it future-proof? Like, can you then maybe modify it for GPUs and so on? So you have to distinguish between the idea, the design, and the implementation. The implementation of MapReduce, like any implementation, is definitely not future-proof. If you stop developing MapReduce and then in 10 years you try to make it work, it's not going to work. The OS will have changed, the hardware will have changed, and so on. So the implementation for sure is not future-proof. What is future-proof, however, is the idea. The idea of organizing your whole thing with a mapping phase, the shuffling, reducing, and so on, like parallel shuffling, parallel shuffling, parallel shuffling, this idea is going to survive very long, right? And then this idea is completely orthogonal to the hardware. You can also, with GPUs and so on, you can absolutely imagine doing that sort of things also with GPUs, right? And GPUs are kind of introducing another dimension, because here is the idea of exploiting the way that a graphical processing unit it has the power to process vectors, basically. So the initial intention of GPUs was for graphics, right, for preparing the pixels on the screen. And then some people discovered that it can be used also for matrix multiplication and so on. And so that's how it appears. And this is some kind of parallelism, in fact, that is local in the GPU. So yes, to answer your question, the implementation it's never future-proof. You always need to maintain it and so on. In fact, now it's superseded by Apache Spark and other technologies. But you will see when I explain Spark to you that the idea is still there. This idea of mapping, shuffling, reducing, you will see it's still in Spark, completely intact. And this is why it was worth understanding MapReduce, because now you will understand Spark as well with the same idea. Right? Did I answer your question? Yeah, awesome.
Now there are some questions on Zoom.
Yes.
So the first question is basically, can any function that takes in a collection of key-value pairs and puts out a collection of key-value pairs be expressed in this MapReduce paradigm?
Yes, because it can, because the function can be anything. As long as the function has the signature that it takes one key value and outputs 0, 1, or more intermediate key values, you can put it in there. Now, I'm not sure if maybe the intent of the question was, can you put any idea as a MapReduce job, right? Can you find for every idea a function that would implement the idea? But if the question is, can you put any function in there, the answer is yes, absolutely. It's your code, you can write your own code, and you can put absolutely any function in there.
Yeah, I think it was more about, can any task, any data task be implemented?
Oh, any algorithm.
Or algorithm.
Yeah. So the reason why MapReduce was so popular is that even though it's relatively simple, I mean, maybe I'm pushing it, calling it simple, but still relatively simple in the fact that it's map, shuffle, reduce, it is incredibly generic, because you can use it to index the internet, the web. You can use it to do matrix multiplication and so on. So it has a lot of application. You can implement the selection, the projection, the group by, the order by. So now, by now, you probably see that you can actually implement a relational algebra and even SQL on top of MapReduce, right? So it's very, very powerful. However, it might be, and it is in fact the case, that for many algorithms, even though you can implement them with MapReduce, you might need several MapReduce jobs. So it's very rare that you can implement something with just one job. That would be rare. But if you allow yourself to have multiple jobs, like you do one job with a specific map and reduce function, then you do another job with another map and reduce function, then you have a lot of algorithms that can be implemented in this way. Yes? So the question is about basically how much, how computationally expensive can the reduce function be, right, in Solver. So here, the idea is always a matter of balance. When you talk about performance, the main idea is that always there is a bottleneck somewhere in one of four places. It's going to be reading from the disk, or it's going to be the memory that is full, or it's going to be the CPU that is at 100%, or it's going to be the data flowing over the network. In almost all cases, it's one of these four. That is your bottleneck. That is your limiting factor. And so if I put the question you asked in that context, the answer would be, you can put as much as you want in the reduce function, as long as you don't start getting into the situation that the CPU becomes the bottleneck. Basically, as long as the bottleneck is reading from the disk, the CPU is not fully utilized, then you can fill the reduce function with plenty of computations. And then you just need to be aware that at some point, when you have put so much code in the reduce function, then the CPU starts being the driving factor, meaning that what's keeping everybody waiting is the CPU, and now the disk might be idle. It might be that now you no longer need to read from disk anymore. And this is when you start asking yourself the question, okay, since now it's the CPU that is the bottleneck, is it still a good idea to be using MapReduce, or am I using it well? Because the design of MapReduce, what the designers had in mind is that it is meant to solve the case where your bottleneck is the disk. If you are running on your machine and you're already reading the disk at maximum speed, this is where MapReduce helps, because it spreads reading from the disk over plenty of machines. Now, if you get into a situation that's no longer your bottleneck, but it's the CPU, you're no longer within MapReduce or massive parallel processing. You are entering the HPC area, high performance computing. And here I have in mind the weather forecast, you know, Meteo Suisse and so on, supercomputers. It's a completely different realm when you enter that realm, because then it's going to be something different than MapReduce. Right? In fact, it's true in general in computer science. Whenever you design a technology, that technology is meant for a specific area or a specific situation. And when you push yourself out of that situation in the way you use it, comes the point at which you might consider a change of technology or a change of paradigm. That really depends on what you're using. Right? Did it answer your question? Yeah, awesome. And keep that in mind, whenever something is slow, it's either the CPU or the memory or the disk or the network, one of these four, and you have to find out which one of the four it is. If you try to optimize without knowing which one of the four it is, you're going to waste your time. Right? So always figure out, is it the disk, is it the CPU, is it the network, or is it the memory?
We have more questions on Zoom?
Yes?
Yeah. So the first one is on a high level. How is this MapReduce related to Google's PageRank?
So you can indeed use MapReduce for PageRank. PageRank requires multiple MapReduce jobs. So one job is not going to be enough. So basically PageRank, it's this algorithm that made Google successful 20 years ago, with the idea of putting weights on the links between web pages, that a website that is very famous and has a lot of incoming link, then will have more weight on its outgoing links, right? In fact, PageRank is a matrix diagonalization problem. You basically have this huge matrix and you want to find some bases in which the matrix is diagonal. Another way to put it in the way that it's implemented is that you need to repeatedly multiply until something converges. So it's matrix multiplications. And it turns out that multiplying matrices is something that MapReduce is very useful for. That we can, because if you multiply a matrix, that can be done in parallel. If you look at the structure of the formulas of matrix multiplication. Right? So you can partition your matrix and basically compute in parallel the values in there. Does it make sense? Right? So it's directly related. You can implement PageRank with a couple of MapReduce jobs.
Yeah, and there's one more. So it's more of a high-level question. What's your take on how transformers from machine learning are, in an abstract way, basically just MapReduce functions over data?
Yeah. So if I oversimplify things a little bit, and first I have to say I'm not an expert in artificial intelligence, but what I do understand about artificial intelligence and transformers and machine learning is that it involves a lot of matrix multiplication. You have to multiply all over the place, and matrix multiplication is basically a lot of addition and a lot of multiplication. So while it is true that you could use MapReduce in order to parallelize this, the idea of multiplying matrices is something so specific and at the same time so widespread in terms of intensity of the money invested that it is worth designing something even more customized than MapReduce. And the idea is really in terms of that's kind of the real world thing. Whenever you're a user of MapReduce or a platform like that, it's a matter of how many resources do you have, how much money do you have. If you're a small startup and you don't have a lot of investments yet or a lot of money, or you're doing your first prototype, it's probably a good idea to just use MapReduce the way it is, or Spark, or whatever technology you want. You're going to ask yourself the question, should I now design my own thing? If you start having a lot of resources, a lot of people, a lot of money, and a lot of machines coming your way, then it becomes worth it to design your own system that is specifically tailored for what you want to do. And since artificial intelligence is such a hype, and large language models and the transformers and in particular matrix multiplication, it's because of this very strong interest and very strong, one of the professors I had at ETH would say Kundennutzen, right, in some course about startups. If you have Kundennutzen, then you have the resources to go beyond MapReduce and implement your own thing. That's exactly what's going on with artificial intelligence. That's why there's this gold rush for all the chips and NVIDIA and so on. It's because there is the Kundennutzen, and it's a very specific case. So this is why we are not using MapReduce. We are going beyond that and designing even the hardware that is specifically tailored for matrix multiplication. Did I answer your question?
I mean, maybe how I was to interpret the question more is the other way around. So if you have now this language model or whatnot, is it in an abstract way somehow the same as a MapReduce task? So not can you use MapReduce to train it, but more, is it in an abstract way the same thing? But maybe I'm misunderstanding the question.
This one I would have to think about. Basically, if you can abstract or see some abstraction behind the transformers that would be kind of logically equivalent to MapReduce, that I would need to think about. I don't think I can answer that spontaneously. But that would be an interesting theory question or fundamental question. I think that there was maybe somebody, if you note down the name, I can give you a pointer. There was a professor in the department who was looking at that from a theoretical computer science point of view. So maybe he would be a good person to ask. Right. I think he's at MIT now. Yes? I think that I think that in the case of matrix multiplication and so on, it's kind of the GPUs that kind of cover that need. I think that a company that started looking into this was Oracle. That they started looking into potentially having hardware that implements this. It is even an area of research. I mean, there are people who are looking in how to use. They do it with FPGAs, for example. How can you use FPGAs in order to implement some of this to make it faster? So yes, there is ongoing research on that, on trying to basically push that down to the hardware. So you basically can see it on 3 levels. You have the purely software or programmable hardware, FPGAs, or hard-coded hardware, if you have the money for that. So it can be ASIC, ASIC, or even printing your own chips. And again, that happens if there are the resources and the money. Like in the case, for example, of Bitcoin mining, there was the money, and so that went all the way down from CPU to FPGA to ASIC and to specialized hardware. But it always depends on the Kundennutzen and if there is some use case in the end that pours investments your way that you can use in order to design that hardware. Yeah. Did I answer your question? Okay, very good. So I wanted to take the time to make sure I answer any question. And as you see, I mean, nobody knows everything, right? I also don't know everything. So I try to answer my best. All right, so I'm going to stop here.